Hi, good afternoon, everyone. Good to see you here. Thank you for coming to our new lecture series. This is the Richard Scheines Distinguished Lecture Series in the Humanities and Social Sciences. And our speaker will be Richard Scheines. I'll pass it on to our Dean Mike Trick to introduce our distinguished lecturer. Thank you.
Thank you. So, good afternoon, everyone. I'm Mike Trick. I'm the dean here, and I'd like to thank you all for coming to the distinguished lecture today. So, at CMUQ, we host these distinguished lectures to showcase the depth and breadth of scholarship of the many experts who visit our campus. Distinguished lectures fall into several categories of expertise, and each of these lecture categories is named after a notable academic from Carnegie Mellon. So, as Sylvia mentioned, um, I can skip one of the steps here. Normally, I say a few words about who the lecture was named for, and then I say a few words about the lecturer. I only have to do this once. So today we are launching a new distinguished lecture series in humanities and social sciences, which we are naming in honor of Dean Richard Scheines. I'm very pleased that Richard is himself has traveled to Doha to deliver the first lecture in this series. Dean Scheines joined the faculty of Carnegie Mellon's newly established Department of Philosophy shortly after Plato um, in 1988. Over the decades, he has been instrumental in shaping the scholarship, leadership, and educational vision of the Department of Philosophy, Dietrich College, and the global Carnegie Mellon community. Today, he is the Bess Family Dean of the Dietrich College of Humanities and Social Sciences and has additional appointments in computer sciences, machine learning, and human computer interaction departments. For decades, Dean Scheines has co led an interdisciplinary research group dedicated to the theory and practice of causal discovery and has applied these methods to educational data. He is the faculty leader of the Simon Initiative, a university wide effort to apply learning science research to measurably improve student learning outcomes. In 2024, he was awarded the very prestigious Doherty Prize for sustained contributions to excellence in education. Please join me in welcoming Richard Scheines to Carnegie Mellon University in Tata.
Thank you, Mike. Thank you, everybody. Can you all hear me in the back? I think this is on. Yes. So it's it's a great honor to have a lecture series named after me. That was a total surprise. So thank you for that. It's been wonderful to be here. Thank you to Sylvia. Thank you to Supriya and all the other staff people who put together and satisfied every possible whim I could have, changing flights, changing hotels, etc. So they were fantastic. And I have to say, I've been involved in one way or the other in discussing or supervising or in some way dealing with what's happening here in Doha for Carnegie Mellon from the very beginning. I was in the debates whether or not we should do this in 2001, 2002. I was for it, I will say, but I don't think any of us were anticipating the degree to which this has been successful, and the quality of the faculty, the quality of the students has been so superlatively wonderful. And I think it's something we are all extremely proud of and grateful to have happened. So thanks to all of you. Thanks to Mike Trick, who's been an amazing dean, friend of mine. So it's really, for me, a great honor to do this. Now, when I originally was asked to do this lecture, the topic I told Mike I was going to do was academic freedom, which has become something of a hobby horse for me as a dean, both painful and interesting. And I changed that topic after we discussed a bunch of different topics and things to one that I think is actually a little bit more appropriate to the topic, which is humanities and social sciences. And in our college, what we've tried to do is cohere the college's mission to be about studying human beings, right? And the two ways that we teach and study human beings involve humanities and social sciences, and they're very different. And the lecture I'm going to give today is trying to be reflective of what are the issues that are of interest about whether or not we can even do social science to understand humans in a coherent and meaningful way. So, outline of the talk, uh, in which I will basically skirt over many of the philosophical issues so high level and so superficially that if you're a philosopher in the room, you will surely object, right? But fortunately, we only have a couple. Um, but I think it's really important in topics like these to give people a sense of the landscape on what are the big issues, what are the big positions, right, that we are staking out to make sense of this, as opposed to going all the way into the weeds and talking about these things in a kind of a depth that will leave most people behind. So I'm going to sketch out things that I hope will be fully accessible. Don't hold me to the depth one would have to go to defend many of these positions at the deepest level. But I'm going to just talk briefly about humanities and social sciences, what they are and how they're different, and then go into the question of whether we can do science on human beings by first saying, well, when is inquiry scientific? Can we do it on humans? And the prima facie answer that many people give, especially the students I teach in philosophy of social science, no, because humans have intentions and free will. And that's not the same as planets and trees, which we can do science on more uncontroversially. And we humans are essentially indeterministic, right? The past doesn't seem to determine what we do in the future. Therefore, we're unpredictable, unlike tides and oceans, which are very predictable. Eclipses, sorry. So then I'll spend a little bit of time getting into what free will looks like and how it affects things, and determinism, indeterminism as a correlator, and then what I think is the most interesting part of the topic, which is predictability, right? Can we predict what humans do in a similar or dissimilar way from how we predict things like planets or galaxies? And then eventually I'll come back to comparing whether we can do things one way on humans and one way on atoms and galaxies, and conclude that you'll have to find out where I'm going to conclude. So the humanities, right, has been a very long-standing tradition on how to understand humans. And the questions humanists typically ask involve meaning, values. What's the purpose of life? What is the subjective experience of the human condition? In evidential and methods, they ask things like, what is the way we're going to interpret various texts, ethnographic studies, historical analysis, social and cultural critiques, creative writing to understand what it is like to be human, how to understand more about the human condition through poetry, novels, etc., and philosophical analyses as well. And the challenges in humanities, as I sort of see them, involve it's difficult to claim objectivity. People have different senses of things, and they don't attempt, in many instances, to say objectively, this is the right critique and this is the wrong critique. This is the subjective experience that's meaningful. This is that's not, etc. And then achieving common standards to compare is also very tricky for humanists. And I've listed on the side some of the easy examples of great humanists through the ages. On the social side of things, the questions are different, right? They involve what causes human behavior? Can we model human behavior, right? Which is a very different sense of things than humanities. What methods and what evidence do we take to be standard in what we use? Well, naturalistic causes, by which I mean non-religious, non-deist, not godlike explanations, but things that we can usually associate with observable and uncontroversial phenomena. Which is not to say that's a privileged truth or a better way to do things, but it's just to say science usually requires naturalistic explanations. Systematic measurement, so we can compare measurements. Experiments, data science, computational simulation. Very different set of methods than you see in humanities. And the challenges are it's hard to measure things about humans in a way that we take to be replicable and objective. The question of internal, external validity comes up often. I won't go into that. And values have to enter. It's hard to assess how they impact things and how that should affect what we're doing in general. So, when is inquiry considered to be scientific, right? Well, again, this is a very, very high-level sketch, and I don't claim that there isn't 6 courses worth of arguments to be had about whether this is the correct criteria, but this is a good first pass, right? Science seeks general laws that explain the empirical phenomena that we can observe. And by empirical, I just mean phenomena that we can all agree, right, is presented in front of us as something we can observe and measure to some extent one way or the other. It requires naturalistic explanations, right? It requires that we make predictions that are empirically falsifiable. If our predictions can be observed, but they can't be falsified because anything we could observe would not falsify the prediction, then that's not considered scientific. So you must be able to say, I made a prediction and it came out to be correct or it came out to be incorrect. And we can sort of agree for the most part on whether or not it was correct or incorrect, depending on the data we observe. And this fourth idea is a little bit more controversial. I won't go into it much, but it's typical to insist that scientific endeavor is self-correcting over time. So if we continually make bad predictions or we continually, right, fail to explain phenomena, right, we tend to require the science to correct itself, to iterate to a different set of theories or a different set of principles. Okay, so what can we say about doing science on human beings, right? Well, again, the prima facie answer is we can't do it because we have intentions and we have free will. Trees do not, right? And that really makes us indeterministic and unpredictable and therefore, right, not scientifically explorable. It's often been claimed that intentions, right, although they're interesting and we function with explaining each other and how we all behave and act by citing intentions, right, are not really observable phenomena. We can't observe your intentions except for you might report them. And again, free will makes us indeterministic and unpredictable, and thus law-like naturalistic explanations, right, aren't possible. So that's the prima facie, right, argument that you get from people who really don't think social science is a possible thing. Okay, so let's start with the easiest topic of all, free will, right? How many of you, let me just get a show of hands, how many of you believe that humans, and including yourself, have free will? That's pretty good. How many believe we do not have free will? It's an illusion. Okay, a very small group. They're the illusion side. Okay, so the questions about free will are legion, but in many senses, what turns out to be the deciding factor is where the burden of proof sits, and I'll get to that in a second. But the typical definition of free will is you chose to do something, but you could have done otherwise, whatever that means. That's a modal. You could have done something differently than you did. So you're free to have chosen the thing you chose and free to have chosen something else that you didn't choose. Then the question becomes, well, what if what you desire, right, and the choices you made are themselves determined by the past and by the way your body and your brain are arranged at the current moment, right? So if that's true, if what you're actually desiring and what you're doing is fully determined by the past and what you're set up to be at the moment, then in what sense are you free, right, and have free will? So that's the challenge that's typically put to people who do not believe we have free will. And then the other question that philosophers have gone into often is, okay, so suppose there is determinism. Is free will just simply incompatible with determinism? Or is there a way to make determinism, even though what you desire and do is determined, compatible with some sense of freedom so that we say, yes, you still have free will? That's called compatibilism, right? And it's very popular among a certain branch of philosophy. Finally, if the world is not deterministic, if it's indeterministic, right, so we don't have to worry about the compatibility problem, right, is the kind of indeterminism that is the world, right, the kind we would need to explain or define or, right, characterize freedom of the sort we experience when we think we're choosing things freely. So it doesn't mean just because the world is indeterministic that therefore we have free will, right? It has to be a certain connection between the way it's indeterministic and the way we think we are not determined to do things one way or the other. So it's a little complicated. So let me go into the free will thing by giving you an example and then challenging those of you who believe free will, right, to say why this is different than what we experience and what we do. And on the other side of the coin, right, the burden of proof will be on the people who say no, right? There's a difference to say what the difference really is, etc. So you've all seen this kind of example, right? If I have a little plant and I have only a source of light above it, right, the plant will grow and it'll go right towards the light. And now suppose I move the light to the side and let some time go by. Lo and behold, the plant bends so that it's pointed toward the light and it gets healthy in that way. And you can see where I'm going with this, I'm sure. Right? Does the plant have a desire to bend towards the light because it needs to get the light to nourish itself? And if I put a barrier in that little black square, that was my primitive attempt of PowerPoint drawing, right? In between the plant and the light source, right? You might say, and people will say this, right, that the plant has a desire to bend toward the light, but can't. So it's not free to do what it desires to do, right? And so you can see how the analogy goes. If we're willing to accept that the plant has some kind of a desire to go toward the light, right? It was free in case number 2 to bend toward the light, and it was not free in case number 3 to bend toward the light, right? But it had the desire in both cases 2 and 3. And so the question is, okay, maybe the freedom that we're talking about is not the freedom to go toward the light, because sometimes we can't do what we want to do, but we have a desire to do it, right? Sometimes the laws of physics simply bind us. We can't fly because we, right, can't defy gravity even if we want to without extra devices. So then it goes back to the question of, well, are the plant's desires themselves determined? And if so, in what sense is this plant executing free will? Well, I think that there are biologists in the room, right? Yeah, so you could probably explain in very great detail uh, why chemically the surface of the plant, right, in case number 2, changes in response to a differential gradient of light on one side than the other, so the plant looks like it's bending towards the light, right? But the plant's desire to bend is determined, right, by the chemicals of the surface and the light and what they do to it. Yeah? So I think in this case, it's pretty obvious that the plant's desires are determined to want to go toward the light by the setup of the circumstance and the chemicals and the way the plant is situated. So here's the burden of proof argument in a nutshell. Is there any serious difference between this case and a case where you form a desire that we can plausibly argue was simply determined by what the environmental inputs were hitting you and the way your brain is organized at that current moment? So if you can say, yes, there's a fundamental difference, then you can say free will is supportable. But if the burden of proof is on you to do it, good luck. Okay, so this case, I'm going to digress into a fun story. One of my absolute heroes of all of science, Hermann von Helmholtz, who lived in the middle of the 19th century and had many, many, many things that were amazing that he did. But among the most amazing was to try to understand a psychological phenomena, which is, how do we tell what's moving, us or the world, right? So if I am standing in front of you like this, right, and you move your eyes to the right of the room, right, the image of me on your retina is going to move because you're moving your eyes, right? But if I move and you don't move your eyes, the image on your retina is also moving. And the question becomes, she's nodding her head because she's known this literature, how do you tell which is which? Well, you have a very clear subjective experience in the room here, where if I move, you're not moving, it's me, right? But if I darken the entire room and it was just, my image, it would be a little more difficult to explain how we distinguish. So let me ask you a question, Jennifer, you can't answer. How do we figure out, right, what is happening when the retinal image moves, right? If it's our eye movements or if it's the right thing in the room that we're looking at. How do we do that detection? Simple question, but it's extremely weird to answer. Nobody really knows this. Yeah.
I assume we just base it on how many other things also move at the same time.
Suppose I isolated the only thing that was in the room in your visual field was me, and I was on a sliding platform that somebody could control.
Then I think you wouldn't be able to tell.
You can tell.
Oh, you can.
You can.
Okay.
Yeah. So if you can detect your eyeballs moving, right, then knowing, oh, my eyeballs just moved to the right, your brain could correct for that, and it could make the calculation that it wasn't the person moving, it was my eyeballs moving. So one option is I can detect the position of my eyeballs over time, right? Now you said the muscles in the eye. Suppose there was a different way to detect the position or the movement of my eyes besides detecting where they are, but detecting whether I intended to move them. Anybody think that might be a candidate for detecting motion? It's kind of a very, very rare hypothesis. So Helmholtz decided that it wasn't just knowing what position your eyeballs were and whether they moved or not that you could correct for the image moving on your retina. He decided it was the intent to move your eyeballs that was going to be decisive. How would you possibly distinguish between those two things? This is where the hero comes in. He could never have possibly passed the IRB. But what he did was extract this chemical from the curare plant, which paralyzes the muscles that you apply it to. And he literally paralyzed his own eyes as a part of the scientific experiment to figure out what was what. These are the kind of heroes we just don't have in the world today. And he discovered, I don't know why, he discovered that if I'm looking at somebody's image, right, and I move my eyeballs to the right, or I try to move them to the right, but they won't move because I've paralyzed them with the curare, that subjectively the image jumps to the left. So the eyeballs didn't move at all. So any ability to detect where they are should be there. But the intent to move them makes subjectively the image jump to the left. So this is the first, in my view, clear philosophical example of detecting intentions and having to make a difference in perception in a way that was undisputable. So any of you who want to stay afterwards, I had some curare, and we can do the experiment all together. Okay, so that's one of the things that was super interesting, I thought. But the experiments that have been going on for many, many decades now that put into question the idea that you are actually exerting free will as opposed to detecting something that you're deciding to do as an illusion of free will started with this guy, Benjamin Libet, in the 60s and have gone on to many, many cases of duplicating the same sort of phenomena. But the basic idea is that you put people in a situation when they're asked to choose something simple, like, are you going to raise your left hand or are you going to raise your right? And then you ask them in a very time frame sensitive way, when did you make the decision to raise your left hand? What exact moment did you say, I'm going with my right hand? Up it goes, right? And then measuring something in the brain and showing that in the brain, right, we can detect the beginning of you making a decision well before you say you're aware of making the decision. So this is something we can duplicate in a number of different ways. And I'm going to be very clear that this does not prove that we have no free will, and it does not prove that we can't decide things. But it does show that our awareness of making a decision is typically after having, in some sense, made the decision. So one of the things you could think of is we're kind of along for the ride, right? It's an illusion that's not real. Okay, so now we're going back to this question of, are the intentions or the desires that we have, right, determined by the past? And if so, are they predictable? And so now I'm going to just go into a little bit more about determinism, indeterminism, predictability, right, which will sort of be the backbone, I think, of what's interesting about this talk. So in determinism, the past of the world and the laws of nature determine a unique future state of the world, right? There's no diverging of pathways. There's no many worlds. There's just one, right? And indeterminism, the past state of the world and the laws of nature do not determine the future. There could be many possibilities. Some of the possibilities might be determined, more probable than others. but probability is not necessary for indeterminism. It's simply that the future is not determined by the past. That's the simple view. Good? Okay. So predictability, totally different idea. And that's epistemological, which is what do we know about the future of the world from what we know about the past of the world. So the past of the world is what it is out there, and we have to measure it, observe it, describe it, something, and so we have a knowledge of the past state of the world. And we have knowledge, to varying degrees, good or bad, of the laws of nature. And if we know something about the past, and we know something about the laws of nature, we can then compute a prediction about the future state of the world. So this is what's involved in prediction, in the way I conceive of it. And then the question of whether we can do something successful in prediction comes down to, once we see how the world evolves, and we look at the measurement we do of it, or the observation we do of it, how does the measurement or knowledge of the future compare with the prediction we made about the future? And so it's this comparison, the knowledge of the future with the prediction of the future states, and the deviation between those two, that really is the story of whether we have predictability or not. Good? Okay, so I will confess I got this generated with ChatGPT, and I couldn't find a good diagram otherwise, but this just shows you a situation where over time, right, we're trying to predict the temperature, and we get better and better at doing that, which is accurate in terms of the long-term history of predicting the temperature. So on the vertical axis is temperature, on the horizontal is time, and the orange dots are our predictions, and the blue band is the average error of our predictions, right, which shrink over time. So we're getting better at predicting temperature in this fantasy of a graph that I cooked up. And then you might ask, well, what are the reasons we have any error at all in our predictions, right? Because every science we do has error in predictions, right? Well, our knowledge of the past might be imperfect. We might enter the wrong data in our prediction about what happened in the past, what the conditions were, temperature in the past, humidity in the past, etc. Right? Our knowledge of the laws that move, right, temperature gradients across time might be imperfect, and our computational power might not be sufficient to the task. In fact, for many, many decades, right, our ability to model the weather, right, was limited more by computational power than by anything else. We could only do volumetric cubes that were 10 miles or more wide, and so we had to be, right, much finer grained, which required much more computational power. Or the world is indeterministic. That's another reason we might have prediction error that's persistent. What are the reasons that we might decrease the error of our prediction over time? Well, our knowledge of the past state might improve. We get better at measuring the past. Our knowledge of the laws of nature improve. We get better at the physics, right? And our computational power improve. We get better modeling capabilities to apply the physics and the past state. Or the world is just stubbornly indeterministic. No, I don't think that's a possibility here, because it does not explain the decrease in the predictability of the situation. There might be a certain kind of indeterminism. We hypothesize it is the indeterminism shrinks over time. Implausible. We won't go with that one. Okay? So far, so good? So on the left, we have either the world is deterministic or indeterministic, and on the top, we have either the future is predictable or the future is not predictable. So which one of those boxes do you think is the most likely to be the state of affairs? Well, if it's a deterministic world, do you think it's more likely the future is predictable or the future is not predictable? Hold your hands up for predictable. Not predictable. Yeah, well, it turns out it's neither one. I've tricked you. And in the indeterministic world, how many think it's more likely for it to be unpredictable than it is predictable? Yeah, again, I've tricked you. It depends on a lot of different other circumstances. There turns out to be almost no relationship between deterministic, indeterministic, and predictability, as I'll get to now. Okay, very roughly, what is it to be predictable? It's when the phenomena, right, can be, right, predicted better and better as our understanding of how to measure the past or the laws of nature or, right, the computational models improve. So the more we know about the past, the more we know about the laws, and the more we can compute, the smaller the prediction error should get over time. Another ChatGPT, which I've been trying to do this example for many years, and I've never come up with a good, I was going to get my daughter to draw it, but she wasn't available, so ChatGPT. So imagine this is a perfectly frictionless, perfectly flat plane that's inclined, no tilt, right, except for in that one dimension. And we can measure where we put a ball bearing on the top of that plane, right, and where it lands on the bottom. So that's the past and the future, and we're trying to predict the future once we position the ball, and we now ask you, where's it going to land on the bottom? And if the ball is slightly differently positioned at the top, right, it's not hard to see that it's probably going to be slightly positioned differently at the bottom. So our past and our future uh, uh, are those, our knowledge of them, right, is not the same thing. So we might not be able to measure accurately where the ball is positioned on the top. We might have uncertainty about where exactly that ball was positioned at the top, right? And we might be uncertain about where it's coming out at the bottom. But if we look and we say, gee, my uncertainty over the top is 0.4 units of measurement, so it's either 1.8 or 2.2 or somewhere in between, I know not which, right? The knowledge of the future is the same kind of uncertainty. It's probably 1.8 to 2.2. We know not. It's in that band, right? And if we improve the precision about where it is on the top to 0.02 or 0.04 from 0.4, then our knowledge of the future is equally constrained to be more precise and better. So this is a classic case of the world is deterministic, fully predictable. Okay, now suppose I have the same inclined plane, but I have some bumps. Like now it's like when you have a grassy field and there's little mounds, right, that you can't really measure in any accurate way to predict. And I say, well, there's the pass, and if I let the ball go, it bounces all around and it lands in that future. And you can see where I'm going with this, I'm sure. If the ball is slightly in a different position, right, and I let it go, it might land somewhere completely different because of the way the mounds are randomly and, chaotically distributed, right? So this situation is a great example of it could be fully deterministic. It is not predictable. Because if I'm uncertain about where the ball starts in the top, my uncertainty about where it lands is complete. I have no idea where it's going to go. And if I increase my precision about the situation on the top, no better in the prediction. And even if I get really precise here, right, this situation is just hopeless to predict because of these little mounds. Right now, if I could measure to the trillionth of an inch or the trillionth of an atom, maybe I could get it right. So maybe it's not in principle fully unpredictable, but in any practical sense, as long as these mounds are shaped in a certain way and small enough, right, any precision boundary on the measurement of the top, right, that's realistic would result in complete uncertainty about the bottom. Right? So this is determinism, fully unpredictable. And this is what really is characteristic of chaos theory. Right? In chaos theory, tiny differences in initial conditions can ramify into humongous differences, right, in the final state. You've probably heard of the butterfly flapping its wings, which I never thought to be an interesting example because I can't imagine how a butterfly really could translate into a hurricane. But that example with the balls, that's more realistic. The three-body problem is a great example of chaos theory. There's a whole TV show and a book named after, which is quite good. So what this shows you is determinism does not get you predictability. It's just too bad, but that's just the way it is. Okay, what if the world was indeterministic? Would that get you unpredictability the other way? And I'm sure you've anticipated the answer is going to be no, because right, it depends on the level of phenomena we're talking about. So consider the case of individual atoms, right? They're typically indeterministic, not predictable. We have quantum mechanics, we have radiation, radioactivity, right? But if I take large collections of atoms, right, and I ask you questions about them, they're highly predictable. So totally it depends on what level I'm talking about. Radioactive decay is a great example, right? We have very, very well worked out theory now that if I have an atom, collection of atoms, and I say, what is the probability that any single atom will decay in a certain time interval, I can give you that probability exactly. Can I tell you which atom is going to actually decay when? Can't do it, and it's even in principle, according to the laws of physics that we think now hold, we cannot do that. But if I give you a collection of atoms, right, I can tell you with incredibly precise boundaries how many of those atoms are going to decay within a certain time frame, right? And if I, know more about the past, I know more about the future in that sense. So I claim, now I'm going to make the connection from atoms to people. It's the same with people, right? If I give you a cup of really hot water, right? So can you see the vapor coming off the top? Is it visible in the picture? And I ask you, right, which of these individual water molecules are going to make the jump into the air to escape from the confines of their cup as water vapor, right? That's their goal. You couldn't tell me. Any individual atom, right, is much, much too chaotic and bouncing around and impossible to predict that I could not tell you which ones are going to jump into the atmosphere and which ones are not with any degree of certainty whatsoever. You guys get the bad seats, I'm sorry. But if I ask you how many water molecules are going to escape into the atmosphere, and I know more about the conditions of the room and the conditions of the cup, I can get better and better at predicting exactly how many water molecules are going to escape. So I have full predictability, right, in the sense I've defined it for the collection of atoms, and I have no predictability for individual atoms, right? So this is what I claim happens with people, right? When I have a large collection of people and they're all consumers, right, and I ask you what will happen when I change the price of some commodity, right, of gasoline or food or something that you desire, which one of you will actually respond to that price change and change your behavior? I can't tell you, right? I can tell you maybe it's more likely, right, because the elasticity might differ according to our circumstances. Mike and I like certain things that you might not, but that's not going to determine whether we'll do it or not. It's totally chaotic and indeterministic. But if I say in a very large collection of people, what will happen in mass when I change the price, I can make very good predictions. And the more I know about things, the better my predictions can be. So it's really exactly the same across people and atoms, in my view. So in determinism and indeterminism, right, the future is predictable in a deterministic world only when we have non-chaotic situations, right? And it's just possible there. It's not necessarily doable, but it's possible, right? And if the phenomena are chaotic, it's in principle not possible to predict. So you can maybe do it if it's, right, and non-chaotic, but you can't ever do it if it's chaotic, given that we can't measure small enough differences to ever do. Yeah.
So I've been thinking about asking you a few times, but I'm trying to. How do you factor a probabilistic view in answering all this, as opposed to it seems to come across to me as a more binary?
Well, if I say let's take the radioactive decay, which is inherently a probabilistic theory, right? And I say I might be in a situation where I don't even have probabilities about what atoms are going to decay over a certain amount of time, right? Then I couldn't predict anything over long stretches of time, right? I wouldn't think, unless I have some other way to measure it. So probability gives me a way to predict the collections, right, of individuals that will satisfy that probability distribution. So if I'm doing quantum mechanics and I'm doing, right, the particles going through a slit and where they'll land on the screen, I can only do it probabilistically. But if I have a good theory probabilistically and I have enough events, it will better and better approximate my theoretical probability distribution on that screen of measurement. So in the way we consider prediction error, right, in probability, it's a bit different, but the observed sampling distribution has to converge on the theoretical distribution in some long-term sense for us to think we have predictability. That's probability. It gives you that. So, is that helpful? Yeah.
I have a question about the idea of separating different phenomena into like non-chaotic and chaotic systems. Don't you think that's a bit subjective? Because let's take gravity for instance and an egg. If you drop an egg, say from this table, we have data from the past that points to the fact that that egg is going to break, right? And if you drop it, say from like this distance down to my hand, it may not break, right? But as humans, there might be other explanatory variables included in that event that we may not know, right? Apart from gravity and distance and a whole lot of other things that we may not consider or we may not know yet, we may not have access to. So can you really say there are non-chaotic systems?
Great question. Let me go to the egg. When you drop an egg and drop it onto a surface and ask whether it's going to break, right? It's not the height that probably makes the big difference. It's the position of the egg, right? So if I positioned it so that it was going to drop at a certain angle, it might not break, and if a different angle. And what I'm thinking is chaotic about that system is tiny differences in the angle of the egg when I drop it will ramify into break or not break, and they're so tiny that we couldn't even measure which is going to go one way or which is going to go the other. So if I drop it from high enough up, it won't matter what, what angle, it's just going to break, which illustrates another feature of chaotic systems. In some cases, certain stretches of initial conditions are chaotic, in which case there's big differences that come out of small initial differences. But other spans of initial conditions are not chaotic. So it doesn't have to be the phenomena of itself, right? There's certain ranges of initial conditions that could be non-chaotic and certain ranges that are chaotic. So the other question you asked, which is, are there other variables we might not have considered, doesn't really relate to chaos theory. Chaos theory says we know everything there is to know about the system, and we know how to determine its outcome from its past. But the differences that are going to cause huge changes in the future are so tiny that we couldn't measure whether you're in one position or another. So it's just a measurement problem in a certain sense that creates this chaotic sensation of we can't predict. Now, there are other situations, like the radioactive decay phenomena, in which the hope would be that if we did know something more about that atom, right, then we could tell you exactly when it's going to decay. Now, that still might be true, but all the physics of the world today, and they've tried this extremely hard for many, many decades over many, many different kinds of things, now believe that there is good reason to think there are no hidden variables that we could measure or that even exist that would tell you, which is to say that according to the current theory of physics, the world is truly indeterministic. It's not a measurement thing, it's not a knowledge thing, and it's just simply the case that there is nothing that we could know, even if we were God, about that thing that would make it, right, predictable. So that's a very strong claim, and I'm not claiming I know it to be true, but that's what the physics now believes to be the case. Okay, so the indeterministic world, in the way I've defined prediction, is certainly quite doable, right, and possible in non-chaotic systems. Economics is one of them, right? And it's certainly not predictable if we have very unlawful indeterminism or we have chaotic phenomena. So it's just really not determinism that gets you or doesn't get you predictability. Okay, so going back now, if we have the system of radioactive decay and galaxies, and we're trying to do science on them, right, which I think all of us would agree there's plenty of good science on atoms and galaxies, right? Can we do a science of the brain, and can we do a science of large human populations? Well, the brain is a kind of a funny example because many people think the brain is a chaotic system, right? Whether you make a decision one way or the other might be down to a very tiny difference in the neural impulses that happen somewhere deep in your brain, and in very, very slight differences in the chemical composition, or the inputs might actually result in a very different decision, left hand or right, or wherever you want to do it. But that's another topic. But in the collection that we're talking about, we do have the kind of predictability that I think we want. So the question is, do we seek general laws? Well, we certainly seek them, right, in the scientific case almost obsessively, right? The idea for a general unified theory of physics has been really, really a goal for many, many decades. And so they really go after that. Do we have it in social and human? I say yes, right? The economics people are trying to get us laws of supply and demand, laws of what behavior we'll see in a market if we have certain preconditions. The psychologists are trying to get us other kinds of laws. They may not be as general and as easy to see as the physics, but they're certainly the goal of those sciences. Right? In some cases, they've succeeded reasonably well. right? Are there naturalistic explanations? Can we invoke something that we understand as natural to explain things in the physical world? Here it gets really interesting because in quantum mechanics, there really is no sense in which we have naturalistic explanations. What we actually take to be fundamental in quantum mechanics is so weird and so counterintuitive that it doesn't really count as a net. So quantum mechanics is certainly scientific, and yet it kind of fails on this naturalistic explanation. What about relativity theory, which is required to actually explain the behavior of galaxies? Does that invoke naturalistic explanations? What about Newtonian mechanics to explain planetary motion? Does that invoke naturalistic explanations? Who says yes? Who says no? Who says, I have no idea what you're talking about? Yeah, you say no. So I would say no, because Newton, when he first came out with the theory of universal gravitation that explained planetary motion extremely well, was facing a lot of controversy because what is action at a distance gravitation? What is it to attract something at a distance? What's the mechanism of that force? There is none. We don't know what it is. So very, very difficult to argue that quantum mechanics and relativity theory invoke naturalistic explanations. What about human explanations? Well, I'd say, yeah, that we invoke human evolution to explain a lot of what we look like and what we do. That's extremely naturalistic explanation. It's just saying we have variation, we survive differentially, we reproduce according to survival adaptation. Economists think we maximize expected utility. That's an extremely naturalistic explanation, even though it doesn't really quite work. Okay? Oh, wait a minute. And on the predictions, they're empirically falsifiable. Yes, for physics, of course, obsessively. They won't even let you publish unless it's fully, right? But they've had some problems. String theory is a good example. We don't really have a prediction we can falsify, and yet physicists love it, so they work on it. And in social science, I say we have plenty of custom and culture about making sure we can generate empirically falsifiable predictions, right? We have lab and field experiments, we have observational studies in epidemiology. They all say, right, we need to make concrete predictions we can test and measure. And if they're not borne out in the world, change something about the science. That is an absolute cultural norm in social science. Okay. Oh, perfect. So I've luckily hit the timing almost on the button. The physical world, I claim, is indeterministic, yes, but often predictable, but not because it's deterministic or indeterministic. Right? And the people, humans, are the same. They're indeterministic, but they're often predictable. And the physical world and people are predictable or unpredictable, depending in the same kind of things on the same sort of the circumstances. Right? So it's whether it's chaotic or not, and whether measurement, right, and probability can actually be used. So I think the room disagrees with me, but I believe that free will is an illusion, right? I can't prove it, but that's my particular belief. But many of you, I think, do not share my belief. That's fine. But what I will insist upon is that either way, right, we can still use science to understand humans. That's my talk.
Thank you very much, Richard. I welcome questions at this point to our speaker.
Way in the back.
I'm so sorry. I have another question. Um, for the charts, the chat GPT charts that you had up about the weather and how over time we've been able to reduce the gap between um actual results and like predictions, like the error, right? So how are we so sure that that trend is always going to continue and it's always going to get smaller? Why can't it get larger? Like, why don't we account for that possibility?
It could. Um, I don't know of any phenomena that I can think of where that's happened. As our understanding of the past and our ability to measure it gets better, and our understanding of the laws better, our ability to predict gets better. The weather is a great example, right? We're much better at predicting the weather than we were 100 years ago, and we're better now than we were 20 years ago, right? Will we ever get to the point where we can predict it exactly? Probably not, right? But I think it's been a pretty much one-way ticket. So can you think of any example where we've gotten better and then gotten much worse?
No, but I'm saying it's not impossible that that happens, because at the end of the day, it's still predictions, right? Yes, it's based on very strong data, very strong scientific methods, but at the end of the day, there's still the possibility that
Well, I will.
the error
Answer
is
that.
much
You're absolutely right. I will answer that a little differently. So, and the weather is the good example. So the weather is now, I think, changing from what it was 20, 30 years ago. There's more energy in the system. And what it turns out to be, because the initial conditions of the Earth are different now than they were 20, 30 years ago, the storms that happen are more violent and less predictable. So I think there is a case to be made that we're now in a range of initial conditions that make prediction worse than it was prior. So I think that when we change the initial conditions from one area to another, we can very much be in a worse situation in terms of how predictable the future is. And I think that's actually happened in the weather. But I don't think besides that, I know of an example where that happens. Maybe you have one? Oh, no. You were asking a different question. Yeah. Then you. Yeah.
And the question you said naturalistic inspiration. Do you see a correlation between sustainability and determinism? Meaning, if the world that builds state, would humans be able to have an explanation for everything given it is that?
Undoubtedly no. But
Has there been research?
I mean, I think that then that gets into what is it to be an explanation, right? So, I mean, the example typically used is with the brain. So if I have, every molecule of your brain in a current moment, right, mapped out and figured out, right, and then I could tell you, oh, I'm going to change this set of neurons firing. Would that explain my getting hungry? Would that explain some behavior? Probably not, right? So knowing the actual immediate, very fine-grained level nature of the phenomena does not necessarily explain the phenomena you're trying to give. So I think explanation is a little bit of a different thing. And it's complicated because explanation is partly an idea that relies on cognitive demands, right? What we take to be an explanation is how we're built cognitively. What might explain something for you might not do it for me, right? Or might not do it for anybody. And I think nobody will argue that quantum mechanics, for example, is particularly explanatory, right? People have just been shredding themselves over it for many, many decades. And now they're like, we just don't understand. You just got to follow the math. And there's no explanations forthcoming. Yeah.
When you were speaking, and I would just say I really enjoyed the talk. Over the slide with the flower, I kept thinking of Kafka's The Hunger Artist. And the rhetorical question at the end, is it determined? What was striking to me was the absence of the scientist in that slide. And I was thinking, oh, yes, well, this is basically torture, right? We're moving this thing to get the plant to react. And who's determining this is the scientist, the moving around, the making the plant. And I remember at Penn State going through the lab and seeing the plants you could touch and make them do things. I'm curious if you could speak. This is a huge jump on the anthropic principle. If you're familiar with it, if
Sure.
okay, if you could speak on that for a second and see how that enlightens the conversation.
Well, it's the anthropic principles we try to actually use, right, the way we think about humans, right, as an explanatory mode or paradigm for inanimate objects like, rocks and this and that. And here's a middle case where it's an animate object, it's a plant, and its response to environmental changes is much slower than ours, right? And yet it's clear, right? If I time lapsed a plant, I could put up a movie in which you are feeling like, oh, that plant's clearly, right, sensing, responding right as it would if we were doing it and we wanted light to the light. So I think we abuse it all the time. We impose, right, human properties and human desires and intentions on everything. We do it in cartoons, we do it in science, we do it in life. So I think it's something you have to do with a huge grain of salt and a huge worry. But I used the example in sort of the opposite example. What I'm saying is, boy, it's pretty tempting as an anthropic thing to say the plant has a desire, right? It wants to go to the light. It executed it in one case and it wasn't allowed to in the other. Now, the question is, the burden of proof is on who? If the burden of proof is on you to convince me, like, what's different about this, right, than the things we could show with humans that are this sort of, it's hard to do. And if you say, well, the burden of proof is not on me or you to show the difference, right? We know we're capable of perceptions, of subjective experience, of consciousness, right? We have pretty good reason to believe the plant is not conscious, although there's dispute about that, right? So then the burden of proof is like, well, even though the plant looks, and of course the same thing with robots and ChatGPT, you could make it look like it's having feelings, right, and experiencing pain, but it probably isn't, right? So then the burden of proof is on the other side. Yeah.
Thank you, everyone. We can continue the conversation outside while we eat lunch. Thank you so much, Dean Scheines. And I'll turn it to Dietrich for some final remarks.
Thank you for that very interesting talk. I'm sure it's going to lead to a lot of conversation. So, thank you for being our first speaker in the Richard Scheines lecture series. I do have a memento to remember this by, and so if you want to come over here and take the memento, and then there is our camera, and we'll take a picture.
Two pictures, two cameras.
Different cameras. Okay, Richard, again, thank you.
Thank you.